Hello everyone, welcome to Hudson Engineering Academy. It's me, your tutor Hudson, and today I'm going to handle one of the most important calculations as far as a civil engineer is concerned. That is to say, mixed design calculations. Because if you go for any construction, you need to know how to do this mixed design. So let's dive in how to handle this from the beginning till the end. Please watch it gently, step by step, you'll understand more. Well, today we're going to have a look at what we call the mixed design calculation. In your concrete technology, you might have learned this, but today I want to show you how can you do a calculation. Suppose you have to do a design and you need a mixed design. So how can you handle that? Now let's have a look at a sample question that I've prepared right here. The question says, we are supposed to cast a beam of dimension 100 millimeter by 150 overall cross section, and the total length of that beam is only 1.2 meters with a minimum reinforcement using the grade of concrete to be M20, and we are taking the grade of the steel reinforcement we are going to use to be Fe415. The question says we have to calculate the mixed design for the above beam and additionally add 3 cubes. That means we are going to cast more 3 cubes of each 150 by 150 by 150 millimeter. This is to help us in testing of compressive strength. Okay, what are the given information? We have the grade of concrete, which is M20, the maximum nominal size of aggregate that we have used in most of our experiments in our laboratories, 20 mm. The exposure condition is moderate. The workability is 75 millimeter slam. Specific gravity of the cement, I did in one of my videos, it is 2.88. These are laboratory experiments that we have already obtained, and these are the questions we are going to calculate based on the results that we have been getting from the lab. Okay. Then the specific gravity of fine aggregate is this, for coarse aggregate is this. Water absorption for coarse aggregate is 0.48%, and water absorption for fine aggregate is 1.1%. So let me take you through the process of doing all these calculations. I will elaborate it clearly so that you get to understand. When doing a mixed design, what you need to take into consideration, the first thing is what should be my target strength of the mix. And according to the IS code, that is IS 10262, that is the IS code that you use for your mixed design calculation. You have to follow it critically. The first step is you need to know your target strength, and it is given by FCK dash, okay, which is equals to FCK plus 1.65 S, or you can use FCK dash equals to FCK plus S. Now, if you take the first formula, that means we need to know the value of S, and in IS 10262 table 2, value of S for M20 and M25 is given to be 4. So you have to substitute here in this formula. Then you're coming with the value of target strength FCK dash 26.6 MPa. Or if you're using the second method, because you have to do both of them and choose which one gives a bigger result. So this is 20, which is the compressive strength of the M20 grade of concrete that we are calculating, because we're dealing with M20. So in that case, that means our FCK is 20. If we are dealing with M25, then it would be 25. Okay. So well, we substitute 20 plus the X value according to table 1, IS code 10262, table 1 gives a value of X for both M20 and M25 to be 5.5. So you substitute here again to get 25.5 MPa. Okay. Yes. So please do follow that. so that you get to know. That's the first step that you have to do. Now, what is our target strength? 26.6, because it is bigger than 25.5. The second step is we need to know the approximate entrapped air amount. Okay, because you're taking the aggregate, and in this aggregate that you're taking, the 20 mm nominal size or maximum size of aggregate that you're taking, according to table 3, okay, that same table for ISO 10262, so table 3, it states that if the maximum size of aggregate is 20, the entrapped air, the amount of air that will be entrapped within this aggregate will be only 1%. Okay, so take note of that. That is table 3 of IS 10262. Now, the next thing is water cement ratio. Go step by step. I will clarify each and everything step by step so that you get to understand it better. Now, water cement ratio, we're getting it to be 0.535. The question is, how do you get it to get to that answer? Okay, here is the table or the figure 1 that help us to get that. Our target strength is coming to 26.6. That means it is around here. Okay, so if you drop this line straight to this, it's coming somewhere here. Remember, this is free water cement ratio. Okay, and this is 28-day compressive strength, which is our target strength for that case. So the target strength is 26.6. Then here it is giving us a free water cement ratio of 0.535 approximately is what I've taken. Okay, so that is clearly how you read that from figure 1 IS 10262. Okay, so that is how I have got this value. Then from this value, you know that the maximum water cement ratio, this table, the maximum water cement ratio is only 0.5. Okay, and to clarify it again, this is the cement we're using is what? Grade 43. That's why we're using the second one curve, because this first curve is for grade 33, this second curve is for grade 43, then the third curve is for grade 53. The cement we are using in our lab is for grade 43. That's why we have used the second curve. Now, the whole of this cement ratio is obtained only for maximum ratio of 0.5. So anything more than 0.5 will be taken as 0.5, not more than that. Okay. Let us look at the next part, which is, I'm calling it part 4, and this is water content. Okay, and this water content is obtained from table 4, and this particular table 4 is basically according to IS 10262, and it says that when the nominal size, maximum nominal size is 20, the amount of water or water content is 186. Okay, yes, so and the unit is kg. That is why I've obtained that water content equals to 186, but this is only for 50 mm slum, and our workability has been given to be 75 mm slum, meaning that we are supposed to have some additional water content that will be added. And how do you add it? For every 25 millimeter slum, you add 3% of that water content. I repeat, for every 25 millimeter slum, you have to add 3% of the what? Of the amount of water that you have. So that means this 186 is only for what? For 50 mm. But our slum is 75. So what is left to reach 75? If I add 25 to this, is what? Going to reach 75. Now that means it's only 3% that I will add, because it is only 125. Okay, so since for every 25, I add 3%, and I'm adding only 25 to reach 75, I will only add 3%. If, for instance, my sum was 100, that means I am adding what? 25 two times. So if I add 25 two times, it means what will happen? What will happen is that here would be what? 2 times 25, and here would go to 2 times 3, which is 6%. Okay? But for my case, it is only what? 25 that I will add to reach 75. I will add to this 50. So I will definitely add only 3% of 186. So this is what you get, and the unit is in what? Kg. Okay? And next is our cement content. And cement content is taken to according to table 5 IS 456. And you need to have this code so that you can do all your what you design well. If you don't have it, then it will what really disturb you. Now, what is the formula to calculate the cement content? The formula is water content divided by water cement ratio. We obtain the value of water content to be 191.58 kg. Water cement ratio, we said maximum should not exceed 0.5. So we're taking 0.5. And this answer is bringing you to 383.2. And this is what? The amount of cement that you have in terms of kg. Okay? Well, now, according to table 5, it gives us a condition. And what is that condition? The condition says the minimum cement content for moderate exposure is only 300. Let me show you that according to the code. This is my code, and this is my grade, M20. Minimum grade of concrete is M20, and the minimum cement content is only what? Supposed to be 300. The minimum, okay? So meaning anything less than 300 will not be entertained. Should start from 300 and above. Now, what have you got? What we have obtained is that we have 383.2. Now 383.2, the exposure condition says that it should be not less than 300. So this is 383 is actually greater than 300. So the 300 is definitely less than 383 that we have obtained. So it is okay. The proportion of volume of coarse and fine aggregate. That is taking you again to table 5 of IS 10262. Okay, I will give you all the tables that you require to do this. Now, this proportion of volume of coarse aggregate corresponding to 20 mm size and fine aggregate of zone 2. Now, the biggest question is that how did you get this zone 2? Okay, this zone 2 is obtained according to table 9 of IS 383. The question is, how did you get zone 2? According to our experimental result, of course, for you to calculate and find zone 2 of fine aggregate, to know that fine aggregate is in zone 2, we have to consider your sieve analysis result. And the sieve analysis result, the sieve number that you consider to get the zone of fine aggregate, the sieve number is 0.6 mm sieve number or 60 micron sieve what? Number. And allow me to show you from the data that we had collected. This is the data. Okay? And according to this data that we have, this is 0.6 mm sieve number or 60 micron. The percentage passing is 48.6. And this is what we have used to deduce that it is in zone 2. Okay? So so why is it that 48.6 falls in zone 2? Now, the codal expression will help us there. What is in the code? Which code is that? IS 383, table 9. So according to that, IS 383 table 9. This is our table 9. Okay. In zone 2, you check this line for 600. Now, that is 48.6 is falling within this range, right? It is not here, it's not here, it's not here, but it is falling within this range, 35 to 59. That is why we have read that the zone of that fine aggregate is zone 2. You need your sieve analysis result for fine aggregate and check this sieve number. Then check where the value for the percentage passing is falling. Percentage passing is falling within this range. And you read, that is giving you zone 2. Okay? Well, now, according to this proportion, it says that the volume of coarse aggregate corresponding to 20 mm size and fine aggregate of zone 2, for which water cement ratio of 0.5 is 0.62. The question is, where did you get 0.62 from? Table 5 of IS 10262. And according to that, so this is my code, and the size of the aggregate is 20 and the zone is 2. So that means it is giving us 0.612. Okay? So that's how you have to read it, table 5. So each and every step you need to know the table and how to read it and what you need to take. So that table is only when the water cement ratio is 0.5. Okay? Yes. Now, we need the value. This is the volume. Okay? This should be in meters cube actually. The volume of what? This is the volume of coarse aggregate. What about the volume of fine aggregate? The total volume is 1. So that means the volume of coarse aggregate would be in respect to 1 minus 0.62. And we take what? This. In terms of what? Meters cube. Okay? Yes. Now, after obtaining all this, we need to obtain what we call the mix calculation. And here we go. The total volume is 1 meters cube. And we say that it is the volume of the entrapped air was 1%. And in terms of volume, it is 0.01 meters cube. The question is, what about the volume of cement? How do you calculate it? It is given by mass of cement. This is mass. Mass of cement divided by specific gravity of cement times 1 by 1,000. So this is the formula, and you must know it for you to calculate it. So the mass of cement is 383.2. Specific gravity of cement is 2.88 times 1 by 1,000. The volume is coming to 0.133 meters cube. Next is volume of water. Same way, it is mass of water divided by specific gravity of water times 1 by 1,000. Now, what is the specific gravity of water? 1. Then what about the mass of water? We obtain 191.58. This answer is coming to 0.192 meters cube. Volume of all-in aggregate. The total volume is 1. If you subtract this one, and this one, you will get volume of all-in aggregate. Okay? So, 1 minus the first one for B minus C minus D. You get this answer. Okay? Now, we know the volume of everything. Volume of all-in aggregate, volume of fine aggregate, volume of coarse aggregate, volume of everything we know. But we need the mass because we need to weigh it. Okay. Now, according to that, this is how to find the mass of fine aggregate, because this fine aggregate and coarse aggregate, the mass are missing. The formula says, take the volume of all-in aggregate. This is volume of what? All-in aggregate. Volume of all-in aggregate. Multiply with the volume of that fine aggregate. This is volume of fine aggregate. Volume of fine aggregate. Multiply with 1,000. Multiply again with specific gravity of fine aggregate. Remember, in the question, all this information, specific gravity was provided. Okay? The volume of all-in aggregate we calculated. Volume of fine aggregate we got it times 1,000, that times specific gravity. The answer that you're getting is the mass in terms of kg. Okay? Next is mass of coarse aggregate. 0.665 is volume of all in aggregate. Then 0.62 is volume of coarse aggregate times 1000, then multiply with specific gravity of what? Specific gravity of coarse aggregate. You're getting 1179.2 in terms of kg. Okay? Now, remember all this we're getting was with respect to 1 meters cube. Okay? Yes. Now, we need to get what could be the mixed proportion or the ratios that we need to consider. Here we go. The mixed proportion is for M20 and water cement ratio of 0.5 is just write first for their mass, what you have got. So after writing, the ratio for cement should always be 1. So we divide everything by the amount of cement that we have, which is 383. So when you divide all this, the ratio is come to 1 to 1.73 to 3.08. This is how you calculate the ratio. And the total ratio, this plus this plus this is 5.81. Someone will ask me, why are you getting the total ratio? It will help us in calculating the next thing. Now, back to the question. The question was telling us to basically do the casting, the mixed design, where if I want to cast one beam and additionally 3 cubes, we need to get the exact amount of cement, exact amount of sand, exact amount of water that we have to use in this one calculation. Well, this is what we have. We are casting one beam and the dimension of the beam is 100 millimeter by 150 millimeter by 1200 millimeter, which is the same as 1.2. And we're casting 3 cubes. Each cube is 150 by 150 by 150. Okay. Amount of the material required. And in this case, this is the total weight that we need to take for the material. This is what we're calculating. I am casting one beam. Okay. This dimension of this beam is 0.1 meter, 0.15 meter, then 1.2 meter. Now, this is just the volume. And if you multiply that, this unit, this 2500 is because the beam is going to have reinforcement. So because of that, we multiply by 2500. But if it is having no reinforcement, for instance, like the cubes, we multiply with 2400. You understand this in concrete, okay? Now, take this and multiply plus 3 cubes times the dimensions, which is the volume, times this unit weight. So you get 45 plus 24.3, which is the total weight is come to 69.3 kg. Now, in this case, whenever we are doing this calculation, they are getting the total amount of material that we need to have, you need to provide 20% extra because there is possibility of wastage. There is possibility of you having maybe a small error in your calculation, but definitely this is to cater for the wastage or any other thing. Okay, so you must take care of that. Some cases we provide 10%, but in our case we're providing 20% extra. So 20% extra means 20% of what we have obtained here. So the total is coming to 83.16 kg. Okay, well, so this is what we have as the amount of material, but we need to know what will be specifically be the portion for cement, for fine aggregate, for coarse aggregate, then also for water. Here we go. Cement is taking on a 1 ratio. So 1 out of the total ratio, which is 5.81. That's why I told you that we are getting the total ratio because it will help us here. So 1 out of the total ratio times the total amount of the material that we need to get. The answer is coming to what? To 14.31 kilogram of cement that we're going to weigh in the lab to do this casting. And for fine aggregate, it is, the ratio is 1.73 out of the total ratio times 83.16, which is the total amount of the material. So the weight of that is coming to 24.76 kilogram. Okay, that is for fine aggregate. Then for coarse aggregate, the ratio is 3.08, which is divided by total ratio times this, you get 44.08. Now the question is, For well-graded coarse aggregate, we are not taking only one size. We are taking two size, different size. That is 20 mm down, then 12.5 mm down. So that means I need to know what should be the amount of 20 mm down that I will take, then the amount of 12 mm down that I will take. I've chosen the ratio of 70% to 30%. Okay, so that means I will consider 70% of 20 mm down, then 30% of 12 mm down. Now the question is, how did you obtain this? This I will make it clear in my next video. I'll explain to you how to do proportioning of this grade to get a well-graded aggregate, coarse aggregate. Okay, so don't miss that video, because I will deeply explain to you how you do this proportion by trying, and you get the right proportion that you're supposed to mix. Now, in my case, 70% of 20 mm down, I'm calling it coarse aggregate 1. 70% is 0.7 times the coarse aggregate that we have, which is 44.08. So the mass of coarse aggregate 20 mm down is 30.86. Then for coarse aggregate 2, I'm taking 30%, that is 12 mm 12 mm down. I'm considering it 30%, which is 0.3 times 44.08. So I'm obtaining 13.22. Okay. Now we know everything about cement, final grade, and coarse aggregate. What about water? How do you calculate for water? Very important. Most cases, people just estimate when they're doing some work outside, but that is not good. You need to calculate it. So here is water. Take the mass of water that you obtain in the calculation and you multiply with the volume. Okay. So mass of water is this, and the volume of this is for beam, then plus these are for the 3 cubes. So the total volume for beam and the 3 cubes that we have to consider. Okay, because one beam times 0.1, 0.15, then 1.2, that is the entire beam, that volume of that beam. Then 3 cubes, each of these dimensions. So if we multiply with the mass of water that we obtain, it is coming to 5.39, and this is now in terms of liters, which is very easy for you to measure. Adjustment, because there is possibility of water absorption taking place as it has been given in the question. To calculate the extra water, now we have known that we have fine aggregate and coarse aggregate, and for fine aggregate we found already what is the mass. Okay, and we found that it is definitely coming to 24.76, and its water absorption is 1.1% according to the question it was given. So 1.1 divided by 100, that is the same as 1.1%. Multiply it by the amount of fine aggregate, plus 0.48 is the water absorption for the one for what? Coarse aggregate. So 0.48 divided by 100, multiply with the 44.08. Now this is extra water coming to 0.48 for in terms of liters. The total amount is, add this plus this, you get 5.874 liters. In summary, this is what we have: cement, this; fine aggregate, this; coarse aggregate, this; then coarse aggregate 2 is this, and water is this. This is what we're going to use to cast this particular beam. Thank you so much. Thank you so much for watching that video till the end. Please, if the video is helpful, do like the video, share with your friends, and above all, subscribe to the Adson Engineering Academy so that you don't miss any of my videos. See you in the next video.